Hi, I'm Matt Parker, mathematician and author, and welcome to the Star Lecture 2020, The Hidden Power of Maths. Now, normally we would be filming the Star Lecture with you in Singapore, but because of COVID-19, we have to do things a little bit differently. But don't worry, it will be just as awesome. So join me as we discover the hidden power of maths. The way this is going to work is I am in a lecture theatre, and this is where the electron was first announced. It was in this room that colour photography was first shown, and it was on this very stage that Michael Faraday stood when they first demonstrated electromagnetism. This is the Royal Institution's historic Faraday Lecture Theatre. We, however, are not going back centuries. We're just going back a few months to in the UK before we had social distancing, and I did some lectures here with my good friend, Dr. Hannah Fry. Today, I'm going to show you some of my favourite parts of those lectures. I'm going to recreate some of the demonstrations just for you, and we're going to talk to some of the top mathematicians and scientists in Singapore to help us uncover the hidden power of maths. But to start with, we're going to look at one of these, a metronome. You may have come across these before. They're used for keeping time when you're doing something musical, and we can use mathematics to try and describe how a metronome behaves. So we could work out the calculations and equations to predict just one when it's going backwards and forwards. We could have three of them all going separately, and we just do the same calculations 3 times over. I'm going to stop that before it gets too annoying. When we were doing the lectures, we had more than just 3. Hannah had 9 metronomes, and they weren't running separately. She'd put them all on one big board, which was placed on rollers. And what happened may not be what you expect.
Okay, let's see what happens when these things are on a bridge that can move itself left and right just a little bit. Okay, so now that these things can move left and right, something a little bit unusual happens, because every time that a metronome is ticking or tocking in one direction, that left and right movement means that the whole bridge will just be knocked ever so slightly left and right. And what that means is that now these metronomes can effectively start listening to each other. They're all now connected by the bridge, which means that very, very slowly, you just see it moving very slightly there, left and right. And very slowly, they start to synchronise with one another. Like a creepy metronome army, huh?
Indeed, that was a creepy and unexpected metronome army. But can we use the power of mathematics to understand what was happening there? I looked into it and I came across the Kuromoto Model. A model in mathematics is just a collection of equations and calculations which allow us to describe mathematically what's happening in the real world. So for example, if you had a single metronome waving backwards and forwards, we can represent that using a sine wave, where the up and down of the wave represents the backwards and forwards of a metronome. And if we had 3 separate metronomes, like what I was doing earlier, we can have 3 separate sine waves. Each one represents a single metronome, and they're not interacting. If we were to all put them on the one board, so they can start to influence each other, we have to add more details to our mathematical model. And the Kuromoto model is where you take each individual sine wave and then you add on the sine of the difference in the positions of each pair of metronomes, which sounds complicated, but if I turn that on, you can see instead of remaining separate, all of the waves merge. They come perfectly into phase, and when they line up right on top of each other, it means the metronomes are moving perfectly in sync. And no matter where I set them starting, they always end up in a single wave representing that perfect synchronization. And this doesn't just apply to metronomes. The same mathematics describes bridges and buildings all around the world. You may have heard of the Millennium Bridge, and when this opened in London, it did not go as planned. You can see it's wobbling from side to side. People had to hang on to the handrail to avoid falling over. And this is the same situation as our metronome army. The bridge is like the board that can move a bit side to side, and the people are like the metronomes, wobbling backwards and forwards and coming into sync. And whenever all the people stepped in unison, they would cause the bridge to swing even more. Back when we were doing the lectures in December, I actually got to experience what it would be like to walk on a bridge like that. I'm over here in the library at the Royal Institution, where instead of very small metronomes, we have a massive wobbly bridge simulator. We've borrowed this from the University of Cambridge. They use it to test things like, full-size bridges. It's a very firm structure with a tray attached to it, which is able to move a little bit side to side. We've got 2 treadmills. I'm joined by Dylan here, who's going to walk on one of these treadmills with me. So if we turn these on, in theory, we'll start walking slowly to start with. There we go. And then should we go up to 4? Let's try a speed of 4. So now we are trying to walk on a bridge which is not staying still at all. And it feels a bit like being on a boat, maybe, where it's moving around and you're trying to compensate for that movement. And it means we have perfectly synced up our walking. And that's causing it to move, I'd say, a concerning amount. Yeah, you're keeping a brave face, but it's terrifying up here. All our movements is causing it to shift backwards and forwards. You can imagine what would happen if you had loads of people doing this on a much bigger structure. You get the idea that the bridge was wobbly. What had happened is when they were developing the mathematical model to predict how the bridge would move, they forgot to include that it was able to move from side to side. And that's the issue with mathematical models. Yes, I can have a nice simple model like I did with the metronomes, but the world is often far more complex. And if we want to properly understand how the world works, we need to be able to model some very complicated situations. And someone who knows all about complex mathematical models is Liang Ze.
Hello and welcome. I'm Wong Liang Ze, and I work here at A*STAR's Institute of High Performance Computing, also known as IHPC. It's my job, and the job of my colleagues, to design mathematical models that explain how different systems in the world work. My work uses statistics and computer-based models to try and predict what a person's personality is like. By personality, I mean aspects like what drives a person, the things they enjoy doing in their spare time, or even if they like bungee jumping. Instead of having to answer pages and pages of multiple choice questions, our personality test just requires a few clicks to predict someone's personality. Believe it or not, all these things can be modeled and predicted using mathematics. And the way we do that is just like how Matt did with the metronomes. We use a computer. The computer I use is this. It looks just like a computer you might have at home. However, some of the models designed here are much more complicated. My colleagues at A*STAR have designed models to predict things like how wind and heat travel through HDB estates to provide us with a cooler living environment. We also use models to simulate the movement of crowds, like how congested MRT stations get throughout the day, or what happens if an MRT train breaks down. And to design complex mathematical models like these, you need a lot of computing power. Instead of an ordinary computer like the one on my desk, we use supercomputers which can carry out 400 trillion small calculations per second. That's about the same computing power as 400,000 smartphones, all in one gigantic computer. And by using such powerful computers, we can design and build mathematical models like the ones you've just seen, to help us understand more about how the world works.
And those mathematical models we've just seen are not only impressive when you first see them, but the more you know about them, the more impressive they get. Because they're not just predicting things which happen the same way every single time. Things like air flowing around a building or people moving through a train station, that can be different every single time. They're random events. And how do you predict something which is fundamentally random? Well, to show you how we can do that, I've got this marble run. And if I take a bead, a tiny little marble, and I drop it in the top, it's going to hit these wooden pegs. It can bounce left or right each time it hits one, and it will end up in one of these columns, which we have labeled from A all the way through to O. I'm going to drop this in a moment. I want you to try and guess now which column you think it will end up in. Just remember the letter of where you think this marble will go. Okay, here we go. I'm going to drop it in the top, and as it bounces down, you see it's going left and right, and we are in C. So if you thought it would end up in column C, congratulations. But don't be too smug, because that was by no means guaranteed. We could work out the probability that it would end up there, but it could have gone anywhere else. And that's the weird thing about probability. We can say with certainty what the percentage chance is, but we can't reliably predict what any one event will do. If I have hundreds of marbles, though, we can make a much better prediction. I'm going to draw on where I think these will all end up. I think there will be very few down the end. I think there will then be more and more and more coming in here, and then fewer and fewer and fewer right out to the far side. We'll see how close my prediction is. I'm going to tip, well, we haven't counted them, I would say several hundred of these in, and we will see how close I am. Okay, there's a few wedged on the way down, and I will admit I missed with a couple. I did not predict that. But this side, that's not a bad prediction. I was a little bit off on this side, but if we ignore that and focus on this side, you can see how close I got. And that's the thing about probability. If we wanted to predict any one of these marbles, that would be very unreliable. But if we want to predict an overall pattern, that is much more reliable. And that's the secret to probability, doing things enough times that you can accurately predict the overall trend. And when I was here with Hannah in December, we were joined by our mathematical friend Bobby Seagull, who showed us a different type of probability with something you might be much more familiar with, flipping a coin.
Hey, Bobby. Oh, it's very good to see you. Okay, Bobby. What have you been doing there, Bobby?
So I've been flipping coins hundreds of times.
Okay.
On a sort of fair, unbiased coin, you'd expect the chance of a head or tail to be 50-50.
Yeah.
So I thought, let me try and test this by flipping a coin 6 times in a row.
So you'd expect 6 times in a row, you'd expect 3 heads, 3 tails, right?
Yes, but sometimes things don't quite work out the way we want them to.
So have you been flipping a coin 6 times in a row, many times in a row?
Yes, Mr. Seagull's a true maths hero teacher, flipping it 2,000 times. No. I had to enlist the help of school students.
Nice.
So we went across London, found students from Westminster Academy, thank you, and students from my very own school, Little Ilford.
And that's these guys here, right?
Yes, exactly, these students here. So we got them to line up, all with a coin in their hand, and flipping the coin 6 times.
Okay.
If they get a heads, they take 1 step in that direction, and can you guess what happens when they flip a tail?
I'm going to go this direction.
You're right. And let's see what happens when they flip the coins.
So this is like a visual representation of the 6 flips. Okay, so that's the 3rd flip there, is it?
Yep, and that's the 4th. You can see wind blowing the ties about. 5th
Okay, so
time.
spreading out every extra flip, they're spreading out more and more.
Exactly. And now, if we get the students to move down towards the graph,
It's like a
you
human
start
bar
to see a
chart.
pattern emerging.
There's a very good, so there's way more people in the middle there.
Yes, and roughly the same number on the tails and the head side, and a few who've got 6 tails and 6 heads.
So these are 3 heads, 3 tails on this side.
Exactly.
These guys must have thought they were very
Yeah.
lucky. And down here, all tails.
Exactly.
Okay. But you didn't just do this once either, did you? I mean, this is like nested, lots of levels to this.
Exactly. So many classes repeating it many times to get us a better data set. So here we see, this is Westminster Academy students.
So, I mean, pretty much every single time we're seeing most people being in the middle, but you always get these bits at the end.
You always get the extremities. But the beauty comes when we try and combine all the information. So here we see all these little dots. They're a student, a proud, hard-working math student. And you put them together and we get what looks like a normal distribution curve.
Ah, and this is what the maths would have predicted.
Exactly.
From the beginning. Very lovely. Thank you very much, Bobby Seagull. Thank you.
And that normal distribution curve is exactly the same as the one that I, well, attempted to draw down here. And it's a visual representation of the probability of a marble ending up in any given column. As you can see, it's far more likely that some combination of left and rights will end up in the middle, and far less likely that all lefts or all right will end up at the extreme points. The important thing is, it's only a probability. It doesn't guarantee it will happen, it just tells us how likely it is. I'd now like to have a look at a very particular prediction based on a probability, where something is 80% likely to happen. And what people often forget is if something is 80% likely to happen, it's also 20% likely to not happen. And when it comes to predictions, it's incredibly important to know the chance of being wrong. So back in December, when Hannah and I were here, we had a very special delivery arrive.
We have just had a delivery of 100 Christmas presents. And the rumours are that hiding amongst these 100 presents, there are 5 brand new smartphones. And one of you gets to come down and open one of these presents at random. So, who wants to come down and... What a surprise. Perfect. All right, let's see who we can find. If you want to come down there, yeah, perfect. Round of applause. What's your name? Yiling, perfect. Okay, Yiling. All right, so if you want to stand over just over there. Now, you're going to get to pick one of these presents completely at random. 5 of them are phones. The other 95, they're kind of rubbish presents, like socks and satsumas. No one wants any of them. And because you only get to pick one present, we want to give you the best possible chance at getting a phone. But luckily, Matt Parker has invented a very special present scanning machine to help you. How many Matts? Look at this.
Right. Yeah.
Amazing.
This is my Xmas Ray Detector 0.80, and what we can do is we can put these presents through the scanner. Actually, do you want to come with me around over here? If you want to stand behind like the conveyor belt over here where they come out, if I turn this machine on and I start putting the presents in the top here, it will try and detect if there's a phone in them. If there's no phone, it just spits them out the same way they went in. If it thinks there's a phone, it rewraps it. Look at that. Ah, that's a winner. So if it says phone, you put it on the table. If it doesn't say phone, we don't care, right? Just down there somewhere. Is that okay? Are you ready? I'm going to start piling them in here. You sort them out. Here they come.
You seem pretty happy with this machine,
I'm very proud.
Yeah.
It is,
how accurate is it?
This machine is 80% accurate.
Okay, 80% accurate. That's pretty good, Matt.
Yeah,
80% accurate. Okay, so then one of these then that's rewrapped as a phone. What do you reckon are the chances that this is a phone? Shout out what you think it is. Okay, all right. Let's think this through then. So, your machine, how accurate is your machine?
80% accurate.
Okay, so your machine is 80% accurate. There are 5 phones in total. 80% accurate means that it's only going to find 4 of them, right? Which does, yeah. Matt, that does mean one phone's going to end up on the floor.
Yes, the downside to 80% accurate is it's 20% inaccurate. But on the upside, 80% accurate.
Okay, so, I mean, you make a good point.
Thank you.
So, okay, one phone on the floor, it's not the end of the world. Still gives you a really good chance at finding a phone. There's something going on there, though. Hang on. Stop the machine. Whoa. Okay, hang on. Matt?
Yeah?
There are way more than 4 phones on that table.
Yeah, it's 80% accurate at both detecting a phone and detecting not a phone.
Are you saying this machine is taking socks and satsumas and wrapping them as phones when they're not?
Yeah, 20% of them. I don't know if I brought this up earlier, Hannah, but it's 80% accurate.
Yeah, but Matt, there's 95 socks and satsumas here.
Yeah.
20%, that's 19 rubbish presents in that pile of phones.
Yeah, but 80% of them are down here. So the problem is, this is 80% accurate. It doesn't mean these are going to be 80% phones.
Yeah.
It just means, and I'd like to recap, that my machine is 80% accurate.
Okay. But right, by the time you're finished, you're going to have, what, 23 presents over here. Only 4 of them are going to be phones. Yep. That gives you a 4 in 23 chance of finding a phone.
17%.
So it wasn't... OK, well, do you want to pick one at random? I mean, you can open it, have whatever's inside. It's overwhelmingly likely to be Satsuma. Well, you can keep it, though. Merry Christmas. Thanks for your machine, Matt.
My pleasure.
Amazing.
80% accurate. Now, just in case it wasn't clear enough there, I should mention that my machine was 80% accurate. Now, the process of accidentally wrapping, well, in that case, a mandarin orange, which in the UK they call a satsuma, and it's a Christmas fruit. The act of accidentally wrapping it as if it's a phone is called a false positive. And in situations like that, the false positives can swamp the real positives, the ones that actually were phones. And this is a situation where the mathematics tells us a different story to what our intuition expects. Sometimes our intuition is correct. So when you go through an airport and you're in security and a buzzer goes off, people don't panic because they know it's almost certainly going to be a false positive. Someone will get their bags checked and it's just some hair straighteners or some lip balm. We know the false positives swamp the real cases. But if you're being tested for a rare type of cancer and you get a positive result on the test, it's very hard to remember that potentially false positives are far more likely than real positives. And in the current climate with coronavirus and so many tests to see if people have or have had the coronavirus, we need to keep in mind there can be false positives. Unless a test is absolutely perfect, it will say that some people have the virus when they don't. And you get false negatives. That's where the test says you don't have the virus, but you actually do. In the case of coronavirus, we err on safety. So if you do get a positive result on a test, just to be safe, you have to go into self-isolation. But unless we understand all the mathematical details of false positives and false negatives, we cannot accurately model and predict the spread of something like coronavirus. So far, through mandarins, metronomes and marbles, we've seen that you can use mathematics to predict what's happening in the world. The next step, though, is to be able to actually control the world using the power of mathematics. And to show you how that's possible, Hannah invited down a lucky member of the audience to try to solve one of these, a Rubik's Cube.
What's your name? George. Okay, how good are you at these, George?
Solved it a few times.
Okay, all right, let's give you a go. We're going to give you lots of encouragement as you go, and we're going to be...
Can I look at it first?
Yeah, you can have a look,
right,
yeah.
Cheers.
We'll be patient with you, though.
Okay. All right. Yeah, I reckon I'm ready to go.
Okay, come on then, George. Come on, George. Hang on, George. Hang on, George. George.
There you go.
Obviously, that was not just a random member of the audience that Hannah picked. That was George Scully, the current reigning UK Rubik's Cube champion. And we are joined once again by George. George,
Hi
good
there.
to see you again.
Thanks for having me on.
Excellent. Now, can you explain to us how you're able to solve a Rubik's Cube so quickly?
Yeah, so the main thing as well to take away is that it's not just about like maths, and it's not like only some people can do it. A lot of people can do it. It's quite accessible. The main thing is that actually is algorithms. So an algorithm, when it's applied to a Rubik's Cube specifically, it means that you're kind of mixing it up using some moves, then putting it back using another few moves. And by doing that, you've actually switched a few pieces on the cube. So for example, if I have this here, notice how this orange sticker belongs in this red sticker, like they need to swap, then these two need to swap as well. I'll use this 14-move algorithm, and then that will like switch them around. And then obviously the more you know, the faster you'll be able to be, and then that's kind of how it works.
So by a 14-move algorithm, you mean there's 14 different twists, and you've just memorized, if I twist it this way and this way and that way, 14 different twists.
It's pretty much just muscle memory, just like piano, except you're kind of, you have to apply it to very specific situations. So that's why you kind of have to memorize a lot of algorithms, then learn how to apply them.
And do you have a sense of roughly how many different algorithms you've memorized that you can use when you see the cube?
Honestly, I'm not entirely sure. It's definitely around 1,000, I think, and that's going across a couple of events as well, because obviously you've got the 2x2, which is slightly smaller, and then you've got up to like 7x7. You've got all different types. So yeah, I think I know around 1,000, maybe a little bit more, but yeah, something around there.
And what's your current personal best time for solving a 3x3 Rubik's Cube?
My current personal best is a 3.31 second solve. Obviously, you get lucky as well. So that one was actually only a 23 move solution, when normally I'll be doing around 50 to 60 moves for a solution.
And what was your time at the last UK Championship?
I won the UK Championships last year with an average, so because they do an average solve, an average of 7.68 seconds.
Okay, so that takes a lot of practice, but anyone can learn the algorithms, just a few of them, and solve a Rubik's Cube slowly.
I believe it only takes around 5 just to be able to solve it. Obviously, when you want to get faster, the more algorithms you know, the more efficient you'll be. Then you combine that efficiency with turning fast, and that's how you become a faster cuber in general.
Thank you so much for joining us again, George.
Thank you. Thanks for having me on.
Okay, so we could take those algorithms that George has memorized, and instead of having to keep them inside a human head, we could put them into a machine. And then that robot would be able to do what George does. So we thought it might be interesting to race George against a Rubik's Cube solving robot. And I bet you're very interested to see how that went.
We're going to count it down, and then you and the machine can both look. Ready? 3, 2, 1, go! Who's going to win? Who's going to win? Who's going to win? Who's going to win? Oh! George, you're letting yourself down.
I know.
That's absolutely incredible.
Poor George did not even stand a chance. Speed cubing is yet another job that's being replaced by robots. But it is a great example that if we take the instructions for a specific task and we put them into a machine, then a robot can manipulate objects and achieve some incredible feats. Although, it does raise the question, how do we get the algorithm, that set of instructions, into a machine in the first place? To look at that, we're going to have to learn about something called coding. And to explore what coding is all about, we were joined by our programming extraordinaire friend, Seb Lee Delisle.
So Seb, tell us about the kind of things that you code.
Well, I like to make really big light installations that are interactive.
Ooh, okay, and we're seeing some pictures of this here. On the side of buildings, no less.
Yeah, see, my ambition really is to replace fireworks, right?
With lasers?
With lasers, yeah, because like fireworks are old technology. Now we've got technology that's just as bright as fireworks. Lasers, super bright LEDs, but all of my technology is controlled by computers.
Okay, so talking about computers then, how do you control these things?
Well, I'm going to show you how we make something called a particle system. So, I've got a browser open. I'm going to do some coding in JavaScript to make some graphics.
You're going to make an algorithm.
An algorithm,
a series of instructions for the machine.
Exactly right. So the first thing I'm going to do is make a single particle, which is essentially just a shape. And we've got to decide what colour that shape should be. Any ideas what colour? Pink. Pink? I think first thing I heard was pink. So I'm going to actually use magenta, which is my favourite type of pink. And it's a very nice bright pink. And the next thing I've got to do is draw a filled-in shape. So let's hear some shapes. Circle. Okay. Square. I think I heard square. Okay, square. So a square is just a rectangle. So let's draw a filled-in rectangle. We're going to draw it at 0, 0, which is the top left of the screen in X and Y coordinates. And we're going to make it 100 wide and 100 high. So let's look at our square. There it is.
So this X and Y that you're talking about there, are you treating this as though it's a graph?
Yeah, so this huge canvas in JavaScript, it's got pixels, and I can identify each pixel by its X and Y coordinate.
Okay, so this is just straight up maths so far.
It's all maths. It's maths all the way down. And I can change this X value, and you can see that the rectangle moves to whatever coordinate I specify for the X position.
As you increase X, this is moving right across the graph.
Exactly. So let's do the same thing for the Y value. You can see it moves down and to the right. Right, so this is good. It's the start of our particle, but it's not moving. It's completely static. So in order to get it moving, I'm going to wrap all of this stuff up in a function, and I'm going to call this function 60 times a second. But now I can do x plus equals 1, which adds 1 to x every time. And now we should have the rectangle in a brand new place every time. We've made some animation.
Doesn't look much like a firework.
No, so we're getting there. So in particle systems, usually the particles are very small. That's the first thing we can fix. Let's just make it really little. Oh. And now let's make some new variables for the x velocity and for the y velocity. But the best part is when I give those velocity values a random number.
Ooh, okay.
So we can do that with the command random, and if I pass in -10 to +10, then we're going to get a random number in the x velocity between those two numbers, and the same with the y velocity. And you'll see now that every time we run it, it
goes in a different
goes
direction.
in a completely different direction.
A random direction every time.
Right, exactly. So that's kind of fun. So we've got one particle. One particle is cute, but really the idea of a particle system is that we make a whole bunch of particles. So now in this next bit of code, I'm doing essentially the same thing, but I'm creating an array of particles, and we get an effect like this.
Ah, that looks like a sparkler.
Right, we're getting there, aren't we?
Yeah.
We're getting to the sparkler. Now, this is an ordinary projector, so it's not very bright. If we want to create something that's truly spectacular, like a real firework, we need to use a laser.
Ah, wow, they're extremely
Right.
bright.
They're really, really bright, aren't they? And so I can adjust all the settings here. I can change the speed, how fast they are.
wow.
Make them fade out over time a little bit. And yeah, I can add some gravity to make them fall
to the
down.
bottom. Amazing. But of course, the stuff that you're really well known for, Seb, is not just you having control of where this is on the y-axis, where it is on the graph, but letting the audience control it.
Exactly. I love doing interactive things. So what I thought I'd do is actually take the sound from the microphone in my laptop and apply that level to the y origin of the particles. And then we could make a game out of it. So here we've got this. You can see the sparkler on the left. Now, it should be that the more noise that you make, the higher this sparkle rises. All right, here we go. In 3, 2, 1, go.
Oh, they're very good. This is it, guys.
It's getting harder. It's getting harder. 10 points, pretty amazing. Oh, that was amazing. That was such a high score. Well done, everyone.
Amazing.
Yeah.
Sam, thank you to you two for showing us all your lasers. That was really
Very,
wonderful.
very welcome.
Thank you very much. Seb.
Thanks a
Thank you.
lot.
When Seb was programming, it may have looked complicated, but all they were doing was typing in the step-by-step instructions to achieve the task. The algorithm. And algorithms can achieve some absolutely incredible things, including making a cup of tea. And of course, we went and found the most advanced automatic tea-making robot there is.
That's a great outfit, Matt.
Thank you. I made it myself.
Yeah.
Sorry, I compiled it myself.
Okay, now, Robot Matt, like all robots, he isn't particularly bright.
Offence registered.
He also takes things incredibly literally, as we are about to discover, because we are going to, together, try and instruct Robot Matt Parker with how to make a cup of tea. Okay, so here we go. What's the first thing to do if you make a cup of tea?
You heat up the water in the kettle.
Heat up the water in the kettle, perfect, sounds sensible. There's the kettle. Okay, next step.
You take out the tea bags.
Take out the tea bags. Sounds good. Next step.
Get a mug.
Get a mug. Oh, it's a teeny tiny one. Teeny tiny one. What should we do next?
Put the tea bag in the mug.
Is that the right mug there? Well, let's get another.
Put the boiling water in.
He takes things very literally.
Heat registering.
Get a normal sized tea bag and cup.
A bigger cup.
Put the normal tea bag in the mug.
I'm going to come around there, hang on. 1 second. Hold on a second, I'm going to come up here. Here we go. What's next? What's next?
Stop pouring the water.
Put the tea bag in the mug.
Pour the water into the mug.
Stop pouring the water. Add milk and sugar to taste.
Pour the milk from the first mug into the mug with the tea.
Okay, I think we've got one more.
Stop pouring the milk into the cup.
And the last step.
Drink it.
I've made this for you.
Here's everyone. Oh, that's that. Thank you very much.
What we've just seen there is an example of both a very handsome and practical robot, as well as something called deterministic programming. That's where we explicitly specify every single step of the algorithm. But as we saw, that can go wrong if there's suddenly a new novel situation we hadn't thought of, and there might be unintended consequences of the steps we've put in that we just didn't think about. Wouldn't it be better if there's a more flexible way to program a machine? This is where something called machine learning comes in. That's where instead of specifying how to do a task, we just tell the machine what the task is we want it to achieve, and it works out how to do it on its own. I appreciate that may sound like wishful thinking, but to prove it can be done, I built a machine named Menace, which was able to teach itself how to play tic-tac-toe.
Menace machine looks quite a lot like a whole heap of matchboxes.
That's because Menace is just a heap of matchboxes. But we've taught these matchboxes to play noughts and crosses.
Okay, talk me through it. How on earth can matchboxes play noughts and crosses?
Well, the great thing about noughts and crosses is there aren't that many possible games. There's only 9 squares, it's a nought or a cross. And on the front of these boxes, every single one is a different state that the game could be in. In fact, this is every possible position of every possible game that Menace could possibly face. We've got all the first moves, second moves, the third moves are in blue, and the final fourth moves are over here in pink. And inside each box, we've put some coloured beads. So here's one that we haven't used yet, and you can see there's a real mixture. There's like 9 different coloured beads, and each colour of a bead corresponds to a move Menace can make.
Because, of course, there's only ever 9 possible places that you could play for noughts and crosses.
Exactly.
Okay, so how do you actually train it, though?
Well, initially, there's just a random collection of beads in every single one. So actually, it's making every possible move equally likely. And initially, Menace is terrible. But the reinforcement learning is we track each game, and if Menace wins, we give it more beads that are the same colour into the same boxes. If it loses, we confiscate those beads, which makes it less likely to do that move again. And to train it, we've had it play hundreds of games. And thank you so much, everyone, who before the show tonight played against Menace. Each time we either reward it or we punish it. And with each game, it gets a little bit better.
And how good is it? Do you think it can beat a human?
I think it will probably not lose to a human.
All right, well, let's give it a go. Who would like to come and play with Menace? Let's go for you there. Yeah. Round of applause as she comes down. Okay. What's your name?
Ali.
Ali. Okay, perfect, Ali. Now, Ali, you've got the advantage of being a sentient being, so I think it's only fair that we let the matchboxes go first.
Okay, so Menace is going to go first, and this is the blank box where there's nothing on it, because we haven't played it all yet. I'm going to give it a shake, and then I'm going to pull a bead out at random. So while Menace is the brain, I've got to do the actual moving around. Okay, so the first bead is green, which is not surprising, because you look in the box, they're all green. There's one purple one, because Menace has learnt very quickly if it goes in the middle to start with, it's way more likely to win. Now, there you are, Ali. Where would you like to go? Put a cross wherever you wish. Oh, a corner. Bold move. Okay. I've now got to find, in the group of second move boxes, this game. Okay. There it is. But if you have a look, Ali, it's the same as this game, but it's the mirror image. And that's because we didn't want to use twice as many boxes. It's not good for the environment. So if you don't mind me turning the game over, are you happy that's still the same game? Mm-hmm. But now it exactly matches what's on the box. So I can give it a shake. And Menace is going to go. Make sure it's properly random. Yellow. They're all yellow. Okay, so it's learnt. I mean, there are other moves it could make, but it happens to have learnt that there is a good second move. Okay, you'll go. Predictable. Okay, you're not letting it win that easily. That's fine. Okay, third move. Where are we? There. Okay, so you can see that one there. That matches this state. Here we go. Give it a shake. Okay. Oh, white. Okay, so the next move is going to be white. That's over. Oh, that's not bad. There you are. You're just not letting Menace have any luck, are you? Okay, that's fine. So now I've got to find this in here. Bear with me. This is exactly as much fun as real noughts and crosses. Okay, I think that's it. Let's have a look. Yes, okay, right. Menace is going to go. Oh, there's not many bees left in this one. Oh, orange. Okay, so I'm going to put an orange one there. And now that move. And now for the exciting conclusion. Excellent. And now we go over there. It's a draw. And the problem with noughts and crosses is if everyone's playing perfectly well, it always ends in a draw. So in this case, I'm going to give Menace one extra of those beads to say that was fine, but I'm not going to give it as many as if it had won.
Amazing. Well, there we go. You managed to draw with a bunch of cardboard boxes. Very impressive. A big round of applause if we can. Thank you.
For the record, that was machine learning. We did not tell Menace how to play tic-tac-toe, just that that's the result we wanted. And machine learning can do so much more than just playing a simple game. To have a look at this, I'm joined by Rosa So from the Institute for Infocom Research, A*STAR. Rosa, how are you doing?
I'm doing great, thanks, Matt.
Excellent. And what sort of research do you do?
Okay, so at our research group, we are trying to develop what's called a brain-machine interface. This is a system that attempts to connect someone's brain to a machine from the outside world. So what we will do is we will implant a small electrode called a microelectrode in the brain of the subject, and he will be able to use the brain signals that's being recorded to control a machine, for example, a cursor on a screen or a robot that can move around.
So you're able to read someone's brain activity and use that to control something in the real world.
Yes, that's right. And so the application for this is for people with severe disability. They might not be able to move any part of their body, but they still have intact brain signals. And so we're able to tap on that for them to control something like a computer or an electric wheelchair.
And how are you able to work out what different brain signals represent? Like, how do you know what the person's thinking?
Okay, so first of all, we will have to tell the subject to do some imagined movement. For example, you can imagine a cursor moving to the right, to the left, up or down, and we will record a set of neural signals while the person is doing that. And from this data set of the brain signals that we record, we will be able to build what's called a machine learning model. And this model will be able to predict the movement intention of the subject as new data is being recorded from the electrode.
So if you have enough data of what the brain's doing, and you know what the person was thinking at the time, you can decode those signals to learn what they mean.
Yes, exactly. So we will be able to predict what the person is thinking and where the person wants to move.
Amazing. And how far along is this technology? Is it still theoretical, or are you already starting to use it in the real world?
So far, we've been doing most of our experiments in the preclinical model, but we do hope to move towards clinical trials soon to validate our technology.
That's amazing. I look forward to one day being able to use my brain to control a machine in the real world. That's phenomenal. Thank you so much, Rosa.
Thank you, Matt.
Rosa needs to collect a lot of data about the brain signals because all machine learning, be it learning how to play tic-tac-toe or learning how to read a human's thoughts, depends on how good the training data was. To demonstrate, I've actually built a little machine which can detect if something is a shoe. If I point it at an actual shoe, it will turn green. Look at that. And if I point it at not a shoe, it turns not green. But this machine learnt what a shoe is when Hannah asked a few members of the audience to come down and help train it.
Okay, so here's what we're going to do. We're going to give you 20 seconds, and I would just like you to draw a picture of a shoe that can scan into the machine. Here we go. 2, 1, stop. Okay, all right, let's turn those around, hold them up to the camera, we'll have a little look. Let's scan these. Okay, so we've got some lacy numbers, some nice, a top shot of a shoe there. This is great, lots of laces. You got some trainers there. This is all perfect. Okay, great, perfect. It's all, I think it's all trained, Matt. So let's give it a go. Let's try your shoes there. Okay, perfect. Spotted your shoes. Amazing, it's great. It works.
Is it detecting shoes?
Yeah, look. Yeah, perfect, amazing.
That's amazing.
That's
So
great.
can I just pop
It's
through and
really
get a
good.
closer look? That's incredible.
Oh, okay.
And it's not failed yet on any of these near identical shoes?
No, that's, I mean, you did all draw
Give us a
very
go.
similar shoes. Let's try this one. Oh, no. So, no, it doesn't detect your shoes at all.
Well, you need a much more diverse range of training. I'm very disappointed in all of you.
I mean, guys, you did just basically draw your own shoes. So let's try again. Turn your paper around, try again, and this time, try and think of as wide a range of shoes as possible. Off you go. 3, 2, 1, stop. Okay, here we go. Let's get this in scanning mode. We're ready to go. Do you want to turn it around, hold it up to the camera? I mean, it looks pretty much like a shoe. This is pretty good. This is great. We've got some high heels, lots of high heels. We've got flip-flops, we've got boots. We've got, some wellies there. This is lovely ballerina shoe. That's great. Okay, perfect. All right, Matt, I think it's good now. I think it's got to be good now. It's got to be good now. Let's, surely this works on all shoes now.
Okay, let's have a closer look at it. Excuse me. Shoe?
Shoe, not shoe.
Not a shoe?
I mean...
Shoe?
That's debatable whether that's a shoe.
It's definitely footwear.
Okay, let's give it a go.
With the right data, it could have detected that as a shoe.
This is true with the right data, but I think the point here is that even when you know to draw as diverse a range of shoes as possible, it's actually just really hard to think of everything.
Just unbelievable.
Thank you very much, Matt, and a round of applause for one of our volunteers. Thank you very much.
Our poor shoe-detecting machine had only been trained on 20 samples, and they were not very diverse. Ideally, you would want thousands or possibly millions or more samples that cover as wide a range of situations as possible. And if you can get very good training data, then machine learning can achieve absolutely remarkable things, including almost human-like behavior, which brings us nicely to artificial intelligence. Could a computer fool you into thinking it's a human? We're actually going to run a test because we have a machine learning algorithm which can write classical music. We're going to see if you can spot the difference between that and a human composition in a game we like to call Is the Bark Worse Than the Bite? Our artificial intelligence system has written some music which sounds like the composer Vivaldi had written it. We've also got an original Vivaldi composition. We're going to play both of them, one after the other, and you have to decide which one came from a human brain and which one came from artificial intelligence. This is the first one, played by a string quartet. Was that music written by a human brain, or was it composed by circuits? You decide. Here comes the second piece. You now need to decide, was the first piece or the second piece the one written by a computer? I can confirm that the first bit of music you heard was written by a human. The second one was the one written by artificial intelligence. If you got that correct, don't be too smug, of course. There was still a 50-50 chance that you would get it right at random. And as we saw before, we would have to test over and over again to see if you could consistently tell which was which, and it wasn't just pure luck. But at least, because lots of people will have gotten that wrong, we know that machine learning can achieve some absolutely incredible things. And machine learning is so powerful because it's basically glorified learning by trial and error, which is exactly how we learn as humans. We make mistakes and then try something different the next time. When you were a child, you may have played with something like this, and you master this through trial and error. Now, obviously, as a professional mathematician now, I know that the cuboid block goes through the rectangular hole. But as a small child, I would have just got one of the shapes and just been randomly trying to see if it fits or not. And we can teach a robot to do exactly the same thing. We can give it one of these, we can give it some shapes, and it's just randomly moving around. It looks like it's doing a terrible job, because it is. But if any of those random movements result in success, it's more likely to make them again in the future. And anything it does which doesn't work, it's less likely to do that in the future. So gradually, it learns what does and does not work. And because a machine can make mistakes so much faster than a human, while it may take a child 18 months to learn how to solve one of these, that robot can learn in under 1 hour. Absolutely amazing. To conclude the Star Lecture 2020, I would like to take a look at what it feels like to be involved in computerized learning. When Hannah and I were here, we got the entire audience to try and solve a problem at random, as if they were a machine trying to learn how to do that task. They were recreating artificial intelligence, which we called artificial intelligence. Not so much AI as AI. And here's how it went.
Okay, Steve, tell us what we're going to do.
So what we're going to do is we're going to get you guys here to represent a random computer attempt at navigating a maze. So what we need to do is get your phones out and go into your browsers. And while you're all going back into there, I will show you the maze, if I can please, Rob. There we are. So what we're going to do, we're going to put all of you in this blue room in the bottom right corner, but we're going to incentivize you to go exploring. So you will get 10 points for each square in the corridor that you get through, but far more importantly, you will get 1,000 bonus points for each of the coloured rooms you manage to get to. So the big prize in this one is get to these 3 interconnected rooms in the top left. If you do that, I will be very impressed. Everything we do at Wi-Fi Wars is competitive, so what we've done is we split you into 2 halves. So you guys on this half of the room, I believe, are the blue computer. And you guys are the much louder red computer. That wasn't fair. That wasn't fair. Yeah, booing already. Okay. So we're going to give you 90 seconds to go through that.
So because there's so many people and we're going to be looking at that big map, it's really difficult to work out who you are, right? So you are essentially each representing a random attempt at winning this particular
Exactly.
game.
So if it was 1 or 2, you could find your way through, but we're going to make that much more complicated.
Okay.
Good. All right. Are you ready? All right, good. Well, let's do a gaming then. If you can send it into their phones now, please, Rob. We'll put 90 seconds on the clock, and hopefully we're going to see that immediately we see you all there appearing. So at the moment we've got a lot of blue and red players for the 2 computers, and already people are getting out. A red person was the first one out, so 1 2 wherever you are. Although collectively, the blue team, I was going to say they're doing better, but by the time I said it, they're not. So actually, the red computer, after 15 seconds, have 6,000 points. The blues, 5,400. No one's found a coloured room yet. And as I said, if you can get to these 3 in the top left corner, if you can get there, there'll be lots of
these
observations.
blues doing very well.
Yeah, they're all going for it. It's going around the 2 main channels, as you would expect. They're sort of more often than not, they're picking the main thoroughfares as they hit dead ends. And actually, we've got a few people who are in the purple room now, so well done to you. I think red was the first, so well done. And for context, for anybody wondering what's going on, what Rob's created is a thing that allows us, without installing anything, any device, any browser, any operating system, to beam games into one of your devices.
Red one's on the
way.
way.
Oh, wow, all right, yeah, good. So I don't know if you know who you are, but if there's a red, if you now are in a green room, cheer. Yeah, it's you. Yeah, so well done to you. You were very, very good. You've got 30 seconds left to do something about it. Nobody's managed to find the orange or the red yet, but we have got a few. Well, we've got another red coming for the green, but a lot more blues actually. So blues might manage to level this up if they can all get in there. But with 20 seconds left, it is 70,000 points to the red computer. Blues, you need to do better. You've only got 60,000 with 16 seconds left. So many people getting stuck in this horrible dead end that we cruelly put in the top right corner. I think blues are going to need a miracle. The reds were louder in the cheering. 10 seconds left, 5 seconds left now. 88,000 for the red computer, 82,000 now for the blue. So that is a win, I'm afraid, for the red computer. Well done to you.
If you would like to try that for yourself, you absolutely can. Not right now, but once the lecture is over, if you get your phone out and in a browser go to wifiwars.co.uk/star, you will see a button that says click here to start, and when you press that, you will get to try and solve a task randomly. But before you do that, thank you so much for watching the Star Lecture 2020. We have seen from metronomes to music, from coins to coding, and from toys to tea making, mathematics is absolutely everywhere. And if we learn how we can use maths to model and understand the world, we can then use that insight to influence the world around us, and it's through that we discover the hidden power of maths. Goodbye.